All right, so yesterday we finished up talking about reductive amination, and we said that this can be used to make primary, secondary, or tertiary amines. It's really versatile, and it's a common reaction. And they said, or I said, the way we do this is we first form an enamine, an imine, or an aminium ion, and then we reduce that to our amine. And we said that the reducing agent you have to use is sodium cyanoborohydride because it's more gentle. It won't accidentally reduce your aldehyde or ketone before it forms that aminium ion. And then we talked about some synthetic strategies, but I'll give you guys a synthetic warm-up problem. Let's do this one. This is going to be a multi-step synthesis. We're going to start with methyl cyclohexane. And we're going to form this. And you've got to use reductive amination. All right, so let's take a look at this and go backwards. First thing I would do is identify those bond positions that used to be CO double bonds. So for example, this one we said might be a good position for a CO double bond, and this position might be good for a CO double bond. So let's draw that intermediate that we must have had. Okay, so it must have had an aldehyde on one end and a ketone on the other.
I think you're one carbon.
Am I missing a carbon?
Yeah, because you should have started going down.
1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, I should have the right number. How are we going to get the two amino groups on there then? We need acid. And then what amine? Dimethylamine, so Me2N, I agree.
And then sodium cyanoborohydride.
Yeah, sodium cyanoborohydride. So we can do reductive amination on both sides at the same time with the exact same amine. So I think that's a really useful way of getting two functional groups installed for the price of one. For which one? Oh, sorry. Me2NH. I forgot my hydrogen. Thank you. Then if we look at this one, how the heck can we make an aldehyde and a ketone from something that used to be cyclic? Ozonolysis. So we probably had methyl cyclohexene, right? And we can do this using ozone. And then what's our workup step? DMS or zinc and water or something like that. All right, now the main question is, how can we get from methyl cyclohexane to the cyclohexene counterpart? So radical halogenation, I agree. And then base selection. What base would be appropriate?
Small base.
NaH.
Yeah, small unhindered base, something like sodium hydride would work well, and there we go. So oftentimes these look more complicated than they actually are. It just requires a little bit of practice identifying the carbon-nitrogen bond position that used to be the CO double bond, but in general, it's going to be going to your more complicated branch. Does that make sense? Okay, so let's do a little bit of a flow chart. I like to make an amine flow chart every time I teach this chapter. We know we can go from amides to amines. We know we can go from nitriles to amines. We know that we can do the Gabriel synthesis and make amines. We can also use NaN3, or we can use ammonia. All right, so let's take a look at the amine we're trying to make and then fill in the boxes for the reagent conditions. So for an amide, what reagent would we need to accomplish this transformation? LAH. So we can reduce it. And H2O, that works. All right, our nitrile, how can we do that? Not quite.
Oh, it's LNH.
all we need to do is reduce it again, right? So same exact conditions. These can be used to make primary amines. What about with the Gabriel synthesis? What's our first step? Sodium hydroxide, we need to deprotonate this proton coming off the end. Then we need to treat it with an alkyl halide. The alkyl halide has got to be this portion, right? And then what's our last step? It's one of two things. We said hydronium, that acid workup's kind of slow, so what's more common? Hydrazine. So that's our Gabriel synthesis. We said that that works really well. It's not as good in terms of atom economy, but it doesn't really matter because this method was bad for what reason? With the sodium azide.
Kill you.
It'll kill you, right? So I'd prefer to have worse atom economy than accidentally die. I don't know about you guys. So if you are one of those people that likes to live dangerously, I suppose you could do this.
I too like the future.
You need your alkyl halide, and then what? Does anybody remember the next step? And we do lithium aluminum hydride and water. All right, and then with ammonia, can we just alkylate? No, that won't work because we'll run into overalkylation. What's another way? Give you a hint, we just covered it.
Oh, do the acid bad and then ketone.
Yeah, exactly. So reductive amination, all you would need is acid. We know that this position right there used to be a CO double bond if we're doing reductive amination, which means that our carbonyl must have been some sort of aldehyde. And then we need to reduce it using sodium cyanoborohydride. And there you go. So these are all the ways we have for making primary amines. All of them work pretty well. I'm going to clean this up. However, you can't get tempted to use alkylation because you run into that overalkylation problem. All right, so let's say we want to make, instead of a primary amine, a secondary amine. I'll call this R prime. How can we accomplish this transformation using the chemistry that we know?
We could still do the reduction.
So if we look at our starting material, right, this part is the same as what we started with. We're forming a new carbon-nitrogen bond right there. So which method do you think will work? Probably reductive amination, right? Reductive amination is like the Swiss Army knife for making amines. So if we go through, this must have been some sort of ketone or aldehyde. In this case, it must be an aldehyde. And then sodium cyanoborohydride. And there we go. So we're able to make a secondary amine. All right, let's continue on. Say, okay, now that we have this, how can we change this into a tertiary amine?
I'm gonna guess you're gonna use it.
You're just going to guess that? It's a solid guess. All right, so if we want to do a tertiary amine, same thing. We do more reductive amination. This time I'm going to use it R double prime. And sodium cyanoborohydride. And then last but not least, how can we go to our quaternary ammonium salt?
Alkylation for the reductive amination.
Ooh, close. You have it half right. Can you make a quaternary ammonium salt from reductive amination? Why or why not?
Oh, it breaks out 10.
I don't know. It's very comfortable. not possible.
Well, think about it this way. We saw in the aldehyde and ketone chapter that you can react primary and secondary amines with ketones and aldehydes, but you can't do tertiary amines, right? So in this case, the fact that our starting material is a tertiary amine means we can't form an enamine or an imine. That means we can't use reductive amination. The only thing we can do is treat this R, now quadruple prime, with some sort of alkyl halide, and that can get you to your quaternary ammonium salt. And you'd have some sort of counter anion floating around as well. Does that make sense? All right, I know these can look complicated. Arguably, you can tell the most important reaction is going to be that reductive amination. However, if you are making a primary amine, there's a variety of different ways. They may show up on the ACS exam, so you want to be familiar with that top branch in particular. Yep.
For making the secondary amine, is it the R that's coming in with that aldehyde that is the R prime?
Yeah, sorry, I should have put an R prime there. Yeah. Thank you. There we go. All right, so let's continue on and talk about some older chemistry that's still relevant to amines. We talked about this previously, but acylation is really important with amines. And I'll show you guys why, but let's say we want to accomplish this transformation. What reagent might we use to make this longer? Yeah, so something like an acid halide. So for example, use acetyl chloride. That would work. What's another route? What's the next most reactive after acid halides? Anhydrides, right? So really either would work to acylate nitrogens. And the neat thing with this is we've really changed the behavior of the benzene, right? If we look at this one on the left, is that going to be an ortho-para director or a meta director? It can be ortho-para. What about this one over here? Is it going to be a strong ortho-para director, weak? Is it going to be an electron withdrawing group? What do you guys think?
Because it's a conflicting resonance, right?
So it can donate these electrons from the nitrogen into the ring or out of the ring. So this is actually a weak ortho-para director. This one is strong ortho-para. All right, another thing too, let's imagine we're reacting aniline, the one on the left, with something like bromine and aluminum tribromide. Do you think we're going to get primarily ortho or para or a mixture of both? So with bromination. So if we try to brominate this, what do you guys think might happen? Yeah, you get a little bit of everything. Where with this one, do you think you're going to get very much ortho? Probably not nearly as much. So this can be a really clever way of kind of toning down the electron donating group on your nitrogen and make it so that you can get more of your para than your ortho. So let's take a look at some of these. I'm just going to erase this for now. All right, there's a couple things. One, we said if you treat this with Br2 and aluminum tribromide, we said that you would primarily get ortho because that nitrogen's not very big and bulky. So statistically, you've got two ortho positions versus the one. And then the other problem is that this is so electron rich that it's really, really hard to control. And you run into the problem of overbromination. So a good workaround would be to treat this with an acid halide or an anhydride, acylate it, then do your bromination, and we said that the para position is sterically more accessible now. And then what if we want to go back to our aniline derivative? What should we do? How can we remove that? It's just an amide, right? How can we cleave amides?
You could probably just crank acid and heat, right?
Acid and heat, exactly. So H3O plus and heat can hydrolyze amides and give you your para-bromoaniline. Without doing that acylation step, you're kind of going to have problems getting para-bromoaniline. You're not going to get very much of it, if any at all, using the traditional techniques. So that's one thing that's really useful.
So since that's an amide, you can use a weak acid, right?
Typically, you need a pretty strong acid in heat, so you do have to be careful if you've got other acid-sensitive functional groups. I'll show you guys the second thing that's sometimes a problem. Oh, shoot. Let's take a look at this reaction. You could be tempted to say, hey, this is just normal Friedel-Crafts conditions. It's electron rich. That shouldn't be a problem. We should get maybe this plus our ortho product, right? However, this really doesn't work. Does anybody know why it doesn't work? Yeah, so maybe you could alkylate your nitrogen. So that's one problem.
Probably could over-alkylate as well, because all of the things are activated.
Could do SN2 on methyl chloride. What was the other one? Okay, over-alkylation. So we've amped it up too much. Does anybody know another one? Give you a hint, it was related to our ACS practice problem today. You already forgot? What is aluminum trichloride? Is it a Lewis acid or Lewis base?
It's an acid as an empty
So Lewis acid, it's got an empty p orbital. Nitrogen has a lone pair. It's a Lewis base. So you can actually form a Lewis acid-base adduct with aniline, which basically sequesters all of your catalyst and will slow down the reaction or prevent it from occurring altogether. So what do you think a good workaround might be, knowing what we know now?
Same thing.
Same thing, exactly. So if you did want to get the methyl group installed para, you'd have to do a workaround. So you could still start with aniline, but first let's treat it with, let's say, an acid halide or an anhydride, doesn't really matter. Then we can do methyl chloride and aluminum trichloride. Why won't this form a Lewis acid-base adduct with aluminum trichloride as readily? I mean, this nitrogen still has a lone pair.
But it's
Yeah, it's resonating, right? So that lone pair is actually somewhat tied up through resonance. It's not going to be as free of a Lewis base. So then
Wouldn't it also be more acidic?
the proton on the amide? Yeah, it's still not very acidic, though. All right, and then last but not least, we can cleave off our acetate to give us what is called paratoluidine, another fancy old school name. And again, this requires acid and heat. Does that make sense? So oftentimes you see acylation just simply as more of a blocking group strategy to prevent unwanted side reactions from occurring. Make sense? You'll oftentimes see acyl groups in drugs as well. I'm not sure if many of you read those medically speaking sections in your textbook, but there is a section where it talks about that, where depending on where the drug is in your body, the pH will change, right? And if the pH changes enough, you can actually pop off an acyl group and turn it into an active drug. So it's kind of a mass drug until it gets popped off. All right, now we get to go way back to first term. You guys thought you were done with this, but you're not. Hofmann elimination. I think it's 1F. I'll have to check. I think it's 2 N's. So Hofmann elimination. If we think back to our chapter where we did E2 chemistry, how did we describe a Hofmann elimination? What product did it give you? Less substituted alkene, right? So E2, we saw it gives you the less substituted alkene. Well, Hofmann's kind of cornered the market on less substituted alkenes, and we'll see how you can make these from amines. So let's take a look at the mechanism. Or before we do, let's kind of do a review. All right, for the top one, we've got an alcohol. How can we get that to form some sort of alkene from an alcohol? So acid catalyzed dehydration, something like that. So H3O plus and heat. What's another way we could get this to work? Tosylate it, right? So TSCl followed by some sort of strong base. But really the key with this is we have to turn this into a good leaving group.
Even though later on.
Yeah, exactly. So with protonation, all you're doing is adding a proton, but that means that water is your leaving group. Water is a good leaving group. And the second one, we're tosylating it, turning it into a good leaving group. So with nitrogen down here, how do you guys think we can turn this into a good leaving group? Protonate it, perhaps. What's another way we could turn it into something that has a positive charge?
Introduce something that lone pair would attach onto, grab a proton, or the positive proton.
Yeah, so protonate or overalkylate, right? We said the big problem with amines is they accidentally overalkylate, but in this case, that's playing to our benefit. So what you can do is treat this with something like methyl iodide in excess, force it to overalkylate, and then treat it with some sort of base and give you your elimination product, right? So that's a clever workaround, is actually purposely overalkylating your nitrogen. So I'll show you guys the full mechanism for this and then the base that's used. Okay, and then we'll talk about why it's a Hofmann elimination as opposed to a Zaitsev. All right, so methyl iodide, we said in excess, will give you these 3 methyl groups, positive charge, and we'd have iodide as your counter anion. You could treat this with sodium hydroxide if you want. Or there's another common reagent that's used. Chem 110 quiz for you guys. What's the name of this? Ag2O. So silver 2 oxide?
Or silver 1.
I don't know.
What do you guys think?
Oh, it's probably silver 1.
Silver 1 has to be silver 1.
Silver 1 oxide, right? Oxygen's always -2. We've got 2 silvers. They must be +1 each. So this would be silver 1 oxide. The cool thing with metal oxides is when you put them in water, they do what? Anybody know?
Precipitate.
They form bases, and silver will precipitate out halogens. So this is a 2 for 1. So I'm going to highlight this and make a note. With water to form H3O, or sorry, hydroxide. And then the silver is going to react with the iodide to form AgI, so silver iodide. And this is going to be a solid. This will precipitate out. So if you remember your solubility rules from Gen Chem, I'm not sure how detailed you got, but a lot of these silver salts are really insoluble. And then we've got our same intermediate, but now we've got hydroxide floating around, none of that pesky iodide. We've got a proton right here. Sorry, I'm going to move this over. And now this hydroxide can grab a beta proton, clamp down, and kick off your leaving group. Plus your trimethylamine in this case. Yep.
So is it the reason we choose this over like acid and then a base to kick off would be because the base would be going to the acid as well?
So you're saying why not do the acid
Yeah, so
one?
like protonate aramine to make it a better leaving group. Because would the base react with that?
Yeah, so you need a base in order to help with the elimination. I think the problem is just the... That's a good question, actually. I'm curious why water won't shove it off. I think water is just not a good enough base to kick off an amine leaving group. Yeah, so you've got to use a stronger base. All right, so now let's look at the Regio Chemistry and try to figure out why this is Hofmann as opposed to Zaitsev. So we've got this amine. Let's try to name it first. What would this amine be called?
2-butane amine.
Okay, so number it. We go 1, 2, 3, 4. Is it an R or an S? S. So this would be S2 butan amine. Okay, so that's our starting material. We're going to do the Hofmann elimination reaction. So our first step, we're going to use methyl iodide in excess. On a side note, chemists more and more are trying to get away from using methyl iodide. Does anybody know why?
Is it toxic?
Super toxic. It will react with a bunch of your biomolecules, including DNA and proteins, and alkylate them, which causes severe problems leading to cancer. So they're trying to phase this out. However, it's still pretty popular. Okay, so now we've got this plus our iodide. In the next step, we're going to treat it with silver 1 oxide. Oh. That's going to help us precipitate out the iodide and help form hydroxide. All right.
I have a question.
Yep.
Is it still a stereocenter at that point?
Yes, it is. Right, because it's just this carbon that's the stereocenter. The nitrogen's not a stereocenter, but the carbon is. Okay, so now if we look at this, I'm going to make you guys do some real review now. We've got beta protons right here. And then we've got a couple of beta protons right here. We've got one that's a dash and one that's a wedge. What I want you guys to do is draw a Newman projection. Oh, you thought you were done with these. Looking down both of these positions, and I'll put a red box for the red view and a blue box for the blue view. See if you guys remember how to do these.
For a second, I was thinking of positive charge on it.
I'm going to do the red one on the left while you guys are working. So if we're looking at this Newman projection, in the back, is the nitrogen going to be to the top right or top left? Top right. So NME3 plus, and then we said the methyl group must be sticking down, right? Which means that there must be a hydrogen over here. Does that make sense? Okay, let's do the blue one now. Blue one, we've got those 3 blue hydrogens, so I'm just going to draw them in the front right away. Doesn't really matter how you orient them because they're all the same. And then let's do the back one. Okay, in the back one, now is the nitrogen going to be to the top left or top right? Top left. Depends on your perspective, but in this case, it's going to be your top left. And that means our hydrogen is going to be here, and we must have an ethyl group sticking down. All right? So, looking at these 2 Newman projections, which one's more stable and why? The blue box or the red box? The blue one, right? If we look at this one right here, we've got this big old Gauss interaction, which means that this is less stable due to Gauss interactions. It doesn't matter really how you spin it, you're always going to have that Gauss interaction for one of those protons, right? In order to get that into the anti-periplanar position. Where with this one, that ethyl group's more or less out of the way, and regardless of how you rotate it, you always have a proton that's anti-periplanar that's set up and ready to do an E2. So, when we finish these, we could say, you know, this is going to grab that anti-coplanar proton, clamp down, kick off your amine. Sorry, I'm going to zoom out a little. And this gives you your kinetic or thermodynamic product.
Hold on, the way we drew that shouldn't take a long right?
Oh, for the blue protons?
Yeah.
Because I don't have dashes or wedges shown, it doesn't really matter, right? They're all equivalent.
Okay.
Yeah. That's a fair point, though. If I had drawn dashes or wedges, you want to be careful. So is this product down here the kinetic product, thermodynamic product, both, neither? What do you guys think? How do we define the thermodynamic product? It's the most stable. We don't care how we got there. We just want the most stable product. So theoretically, you could say, hey, if we did this one, which we know isn't likely to happen, we'd end up primarily with this box. However, it's really not observed because that's has to go through a pretty severe Gauss interaction. We get the one on the right. So this one is our theoretical thermodynamic product, where the one on the right is our kinetic product. It's a kinetic product because it's a more accessible product. It's got the lower activation energy required to get there. So if you do want to do Hofmann elimination, you can do it really easily with an amine by over-alkylating it and then treating it with a strong base or silver 1 oxide. I know you can do it with other leaving groups on there, but I did want to show you guys the Newman projections to explain why this works and not just have you accept it by name alone. All right, I think that's where we're going to stop today. The new pod is a little bit tricky, but try to work with the group and see if you can solve it. I think you guys are at the point where you can start doing some of these trickier pods. If you're stuck, though, feel free to email me or stop by my office, and I'll give you a hint.